Section 2.8 is on two variable inequalities. The graph of a linear inequality in two variables is a region of the coordinate plane bounded by a line. This boundary divides the coordinate plane into two half planes. So as you can see here in these two graphs, in this case the dashed line on the left and the solid line on the right, that's the boundary. And then each side of that line is considered a half of a plane. If the inequality contains the points on the boundary, it's a less than or equal to or a greater than or equal to, then the line is solid. If the inequality does not contain the points on the boundary, and that would be a less than or a greater than, then the line is dashed. And then there are two methods to determine which side of the half plane gets shaded. So which side of the boundary, which half plane are you going to shade? The first method is to choose a test point that's not on the boundary. And if the boundary line doesn't go through the origin, then use 0, 0. If it makes the inequality true, then you shade the side of the boundary that contains that point. If it does not make the inequality true, then you shade the other side of the boundary. Second method is to write the inequality in slope-intercept form. If the inequality contains a less than or equal to or a less than symbol, you're going to shade below the boundary line. If the inequality contains a greater than or equal to or a greater than symbol, you're going to shade above the boundary. Because if it's written in slope-intercept form, you're asking yourself, where is the y-axis? Where are the y values greater than or less than that line that you drew? Let's take a look at an example here. Here we have to graph y is greater than 2x plus 3. So the first thing I'm noticing is that I have a greater than symbol. So that means that I'm going to have, my line is going to be dashed. It's not solid, so it does not contain the points on the line. And since my inequality is written in slope-intercept form, I'm going to be shading above the line. And now recall, basically what we're going to do is graph the line y equals 2x minus 3. So I'll start with my y-intercept of negative 3, and my slope is 2, which means I'll go up 2 and right 1. And I will do that several times here. I can also go down 2 and left 1. And since this is dashed, I'm just going to put little dashes in between my dots. And I'm going to be shading where the y-axis is above the line. So that's going to be all of this area over here, this whole half plane right here. Okay? Here's a word problem that we can use an inequality to illustrate. You put up a new bookshelf that is 1 foot wide to store some of your books and your trophies. Each book takes up 1 inch and each trophy takes up 3 inches. We need to sketch a graph to show how many books and how many trophies we can fit on the shelf. So to start, I'm going to identify a couple variables. I'm going to say let x equal the number of books, because that's basically what it's asking me, is how many books and how many trophies, and I'll say let y equal the number of trophies. So let's go ahead and write an inequality here. So every book is 1 inch and every trophy is 3 inches, and I have a total of 1 foot. Well, I need to convert that to inches. So I have a total of 12 inches that I need to fit stuff in. So 1 inch times the number of books that I have plus 3 inches for every trophy that I have has to be less than or equal to 12 inches. It can't be more than 12 inches because then things will fall off the shelf. So it has to be less than or equal to 12 inches. So let's go ahead and I'm going to bring this down a little bit more. Let's label our axes. So down here, I'm going to have books. And I'll just go ahead and number these 2, 4, 6, 8, 10. And over here, I will have trophies. And I'll go ahead and label those 2, 4, 6, 8, 10. Okay, now I need to graph this inequality. Well, one way I could do this, since it kind of looks like it's in standard form, is I could go ahead and use y-intercepts. So when x is 0, my y is going to be 4. And when my y is 0, my x is going to be 12. So that gives me the point 0, 4. but 12 isn't going to fit on my graph. It's going to be out here somewhere. The other way I could do it is I could turn this into slope-intercept form. So I'll do 3y is less than or equal to negative x plus 12, and then dividing both sides by 3. Y is less than or equal to negative 1/3 x plus 4. So there's my y-intercept of 4. And then if I want to graph using my slope, I'll go down 1 and write 3. And that does get me to 12. And this can be a solid line because I can have exactly that many. Because exactly 0 books and 4 trophies, that's going to give me 12 inches that will fit on the shelf. Okay, so what is the area since this is less than? It's anything that's in this region here will work on my shelf. Anything shaded or anything in this area here. Okay, so actually what that means is that so I can have, this point would mean I can have 0 books and 4 trophies. This point right here means that I can have 3 books and 3 trophies, or 6 books and 2 trophies. Okay, so question I would have for you is it possible to have 5 books and 3 trophies on the shelf? So 5 books would be right here, 3 trophies, that would correspond to this point right here, and that is not included in the inequality, so no, that's not possible. Any point down in here is going to work. Now this is actually kind of interesting. So anywhere, like any of these here, those are all going to work. I could even do some zeros if I wanted to. But the strange thing is I really can't have like 4.5 books and 1.5 trophies. So technically we would just go with the integer values that are underneath that line. Absolute value inequalities, can be graphed in the same manner. So let's take a look at this example. Here I have y is less than or equal to the absolute value of x minus 2 and then plus 1. So let's go ahead and evaluate this. So this is, it's a less than or equal to, so it's going to be solid. And it's written in what looks like slope-intercept form, or similar to it. It's basically solved for y. So this, since it's a less than, it's going to be shaded below. Now I need to graph the absolute value function. Well, looking at this, I can see that my vertex is going to be the point 2, 1, and a is equal to 1, so the slope of my sides are going to be 1. So I can plot the point 2, 1, and my slope is 1, so it's going to go perfectly diagonally through these boxes. Okay, I'm not going to fill all of those in. Connect them with a solid line. And then my shading is going to be below. It's going to be all of this region down here. And that's what an absolute value inequality looks like. We can also go reverse. So given a graph, we can write the inequality for this. So the first thing I'm noticing is that it is shaded above and it's dashed. So that means I'm going to have a greater than, not a greater than or equal to. Next thing I want to do is identify my vertex, and that's going to be the point 2, 1. And it looks like the slope of the right-hand side appears to be 1, so that's good, so I don't have an A. So my inequality is going to be y is greater than the absolute value of x minus 2, because remember it's minus h, plus 1. And that's the inequality for that graph. So in this section we took a look at absolute value two variable inequalities. So linear inequalities as well as absolute value inequalities, how to graph them, and then how to write an equation from a graph.